All right, welcome. In this video, I want to continue our analysis discussion, but now I want to pivot and talk about recursive analysis or recursive algorithms. And so in this video in particular, I want to just take a quick look at what a recursive algorithm is, maybe look at an example, and that's just to refresh us for those of us who've probably already encountered recursion in some form or another before. But of course, our focus again is on analysis. So we want to then think about, well, what is this doing and how long does it take to do it? So the first thing I want to do is again just remind ourselves, refresh ourselves, what is a recursive algorithm? Well, a recursive algorithm, I'm going to sort of define it in terms of a recursive function. A function is something that's a little bit more formal than an algorithm. And so here we can think of a mathematical function as being one that's defined in terms of itself. But we're mostly, CS background, computer science background, meaning that we've probably first encountered recursion as a recursive, procedure or method that we've written that, and in that sense, or if we think of a function in that sense, then this would be a function that calls itself. So a recursive function is a function that calls itself. And then maybe if we want to define what a recursive algorithm is sort of in reference to that, we would say that a recursive algorithm is one that tries to solve its problems using recursive functions. And as is probably common with your own experience, that when we want to define something recursively like this, there's a problem with recursion, which is that it is self-referential or reflexive, meaning we look back upon ourselves. In this case, the function calls itself. And the problem with that kind of circular relationship is if we don't terminate it at some point, it can go on forever. We can keep going around that circle forever. So usually what that means is we can think of ourselves as having well-defined recursive definitions, ones that make sense. When we say it's well-defined, that means it makes sense to us. And then we could have non-well-defined recursive definitions. And a non-well-defined definition would be something like T of n is equal to T of n. It's true, but it doesn't help us understand or learn anything more about T of n. And so in recursion, and when we think about this programmatically, we usually break the recursion into two pieces. One is sort of a terminating a case, a part that doesn't call itself, a piece that will stop, basically stop that infinite recursion. And then the other part, which will call itself, where we hope that there's some sort of relationship between these two parts, where that eventually, if we're calling ourselves recursively, that eventually we'll get to the terminating case and stop. Otherwise, we run the risk of being caught in an infinite recursion, which is very similar to an infinite loop, which means it'll go forever and never terminate. So my example, maybe this is an example that you've encountered in your previous studies as well. Certainly, I hope you've encountered the Fibonacci series. The Fibonacci series or sequence is a sequence of integers that is defined recursively. It is naturally been defined recursively by the famous Italian mathematician Leonardo Fibonacci. Here I've got a definition. This is slightly maybe different than the one that you've seen before, but I've put it in a particular format, and this is the formats of a recurrence relation, which we'll see a little bit more detail here in a second. But taking a look here at this definition that I've got, you'll notice it has its two parts. And these two parts are related to the two parts I mentioned above here. A non-recursive terminating case, what we're saying is if you want to know what Fibonacci number n is, for any n's that are less than or equal to 1, specifically here we're focusing on 0 and 1, you get 1. So the first two numbers in the Fibonacci sequence are 1 and 1. So 0 and 1. And if we want to think about, this doesn't make as much sense, but what Fibonacci negative 1 is, well, according to this definition, it's also 1. And Fibonacci number negative 100 is also 1, according to this definition. And that's the part that's going to get us started off, the non-terminate or the non-recursive terminating case. And then what's left when n is greater than 1, this handles all the other cases, we have a recursive definition. And we can tell it's recursive because f is defined in terms of f. So f shows up on both sides of the equals basically, and that makes it reflexive, meaning it focuses on itself, but also recursive, and that's sort of the property we want to focus on here. Now, as I mentioned before, we could get into a problem here. If we had f of n is equal to f of n, that would set up one of those circular recurrences that would never be able to terminate. But in this case, because f of n is determined by other f's, but f's of smaller values of n minus 1 and n minus 2 in this case, that we can see that those values will keep getting smaller, 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 smaller until eventually, even if this recursion is very big and deep and has many levels of it, eventually subtracting 1 every time, n will be reduced to 1. And same thing by reducing 2 every time, n will be reduced to 1 or 0, depending on whether it was an even or an odd n. And in both those cases, we would end up terminating back at 1 again. So we can see here that this definition of the Fibonacci sequence is indeed a well-defined recursive definition. Again, well-defined meaning we can understand what it means, and recursive meaning that it is defined in terms of itself. Okay. Now again, we've probably encountered this before, and we maybe have even encountered a way to calculate Fibonacci numbers, but usually the way we calculate Fibonacci numbers, if we've been doing this in a math in a math class, we probably wouldn't recursively compute them. In fact, recursively computing things is not usually the natural way that humans would want to solve a problem. It might be more natural for a computer, but when we normally compute the Fibonacci sequence, we usually just start at 1 and 0, if you like, with 1, 1, and then we just do what this recursive definition tells us to do. Take the last two, add them together, and that will give us the next one. And we usually just follow sort of a stepwise pattern to fill that in. But what I want to think about here is saying that, well, the Fibonacci numbers have this natural recursive definition, and we can exploit that by creating a recursive algorithm off of this recursive definition. Now, this recursive definition, again, is the nature of the Fibonacci sequence, and there's not a lot of mathematical definitions or other definitions out there that, by their very nature, are recursive. And by that I mean we might have definitions that we could translate into being recursive, but the Fibonacci sequence is just naturally a sort of a recursive definition. And this is the one that we usually use as our examples. And so what I want to do is say, how do we translate that into an algorithm that is also naturally recursive? Now, luckily, when we're doing this, when we already have this recursive definition here, the process of translating this into a recursive algorithm is actually very straightforward, and in fact it's really just reading it right off. And so I'll sort of go quickly once, then we'll take a look at a code and see how it works. So first of all, if I'm going to write a recursive Fibonacci function, a method, a procedure, something that's going to compute this for me, I'm going to take the input n, of course. So let's call it Fibonacci of n. Okay, Fibonacci of n. And we're going to take Fibonacci of n, and then I'm going to look over here and I'm going to just do my first test. If n is less than or equal to 1, I'll just return 1, and I'm done, because those are the easy ones to calculate, right? Otherwise, if n is greater than 1, what I'm going to do is rely on the power of recursion. I'm going to call this same method again to compute Fibonacci number n minus 1. I'm going to plug in a smaller argument. Same thing for this one here. I'm going to plug in n minus 2. And then I'll take whatever's returned by those two calls, add them together, and return that. Okay. Basically, I'm just reading off what it says here. Now, I've written some pseudocode here for that, and let's just make sure this matches what I just said. So this says we're going to do Fibonacci of n, okay. The first line is just testing like my terminating condition up here. And if you were taught recursion in a more programming perspective, usually you're told, well, the first thing you should do in your recursive code is check for the terminating condition or conditions if there's more than one. In this case, there's technically more than one, but I've bundled them all in this less than equal to. Usually, if you see a different version of this, you might see if n equals 0, return 1, if n equals 1, return 1, and only sets up the 0 and the 1. My sort of natural instinct I've been working with problems and algorithms for a while, is that, well, I'm just going to capture some out of bounds conditions as well. Maybe someone calls me with a strange n minus 5. Well, I've just defined those to be 1s as well. But once you get into the range that most people are interested in Fibonacci numbers for, 1 and greater, then my numbers will match up as well. Okay, so my terminating condition here actually does capture technically infinite values of n, although we were really just bundling it in there to try and capture the first two that start off the Fibonacci sequence, the first two ones. Okay, now that was the first bit here. Now I mentioned that the other thing I needed to do in this next case, which was the other case, well, I didn't put the if there, I just put an else, okay, because that's just the otherwise case. And then, since there's not too much, extra work I need to do here, I kind of just bundled it all on one line in a return call. I said otherwise, so on this line I'm returning 1, on this line I'm returning, okay, making sure I'm copying this down right, this was a recursive definition for my function, but I'm going to translate that into a recursive call. So this is a function call back to this exact same function, but with a smaller n minus 1. Okay, remember I said we don't get a well-defined recursive definition up here if we have f of n is equal to f of n. Well, we run into the same sort of problem here with the recursion in our computation. Then if we called f of n again, we would just get in an infinite cycle of calling the same thing over and over again. That's not going to help us get anywhere. So of course we want to be careful that we're approaching that terminating case. Usually that means getting smaller. Often our terminating case is 0 or 1, so usually we want to get smaller and smaller until we get there. Okay, so we did that here. This recursive call represents this recursive bit of the definition. This one, of course, stepping in for this one. I add them together. That's all in a return. So that all happens. So what we can see here is that the recursive code that, or pseudocode technically, that I've created here is very similar in structure to the recursive definition that we had for our Fibonacci series or sequence. Now, this idea of being able to take some sort of recursively defined idea, mathematical idea, or maybe problem statement, and translate it into a recursive algorithm is following an algorithm design technique called divide and conquer. And that technique is a technique that I explore in a lot more detail in a different video series, my design and analysis of algorithms series, of which this particular video series is intended to be sort of a smaller or minor introduction. Okay, and so here we're just dipping our toes in it, but if you want to, when we're done with this series, watch the last couple videos of this series. If you want, jump ahead into that other playlist, and the first couple of videos will seem a little bit of review to this material as we get ready to tackle more interesting divide and conquer algorithms. This is a divide and conquer algorithm that we've got here, but a little heads up, this is actually a very inefficient way to calculate Fibonacci numbers. If you go and type this in Python or Java or whatever your favorite language is, go ahead and try it. Just try small values of n even. You'll find that it's very inefficient, takes a long time. If you throw a few print line statements in there somewhere to just sort of log what you're doing. In fact, if you put one print line in right as you enter the Fibonacci sequence saying what n is, just print out n every time, you'll see a very interesting pattern of what gets spit out when you do this this recursive call. And again, I suggest doing it for a small value of n, because if you do it for, say, even n equals 100, you're probably going to be waiting an incredibly long time, maybe years, maybe centuries, maybe until the end of the universe. I can't really remember the math there, but it's somewhere between a few minutes and the end of the universe. So if you have that much time to wait, go ahead, but I recommend doing it again on small values of n. Now, if you're thinking to yourself, hey, wait, I think we know what Fibonacci number 100 is, so why does it take so long? Well, like I said, this is an inefficient way of computing it. There are more efficient ways of computing it, of which you probably already know a couple. So you could probably go write a little bit of pseudocode that does it more efficiently than this as well. And well, again, I'll leave that for another video to talk about. But now that we've got this code, I want to kind of go the last step, which is really what I was just hinting at there, which is I want to take this and start counting, well, how many operations are carried out by this recursive algorithm? So that's really what the last several videos I want to talk about here in this series is how can we now start analyzing the number of operations of recursive code. We looked at iterative code and we found with iterative code, iterative meaning looping structures like a while loop, a for loop, and so on. When we use those, we use summations to capture the number of operations carried out. And so we're going to try to borrow from that as well a little bit here, which is if we could use summations, we want to. However, every once in a while, the tool we want to use maybe doesn't immediately fit. In this one, in this particular example, it might be pretty hard to get some summations. You know, if we're clever, we might be able to get it. But instead, what we want to do is we want to rely on, well, this recurrence relation, which is how we define the Fibonacci sequence in the beginning of this video. But I'm going to use it in a slightly different way now. I'm going to use it as a tool that tells me how many operations will be carried out if we call this function on n, our input n. Okay, and again, we call this recurrence relation. So I'm going to just start with a quick little definition here. We talked about at the beginning of this video the definition of a recursive algorithm or a recursive function. Well, here a recurrence or a recurrence relation is just a recursively defined mathematical function. So we've actually already seen one of these. The definition of the Fibonacci sequence we just looked at is an example of a recurrence. Now, usually when we're analyzing some code like this, we're going to use a different name for our recurrence. When we were just looking at normal analysis of iterative code, we started using f of n. That's just because f stands for function, and that's just, we borrowed that more from math than anything else. But here we're going to use t of n. The t here stands for time. And so this has a little bit more of a computer science inspiration, I guess. The t here stands for time. And here we actually usually use the capital T instead of a lowercase one, because it, at least for us, it's going to signify to us that this is a recursively defined thing. It's not like an f of n or a g of n, where usually those are already simplified down. When we're done with t of n, if we've simplified it away so that it's no longer recursive, we'll often change its name to f of n or g of n, something smaller once we've finished. But for now, we're going to stick with a recursively defined recurrence relation. Why? Because, well, we have recursively defined function. It makes sense. Just like the pattern matched when we developed the pseudocode, the pattern is going to match very closely as we develop this recurrence relation. When we want to come up with a recurrence relation that expresses the runtime of our code, because our code has two cases, a terminating case and a recursive case, our recurrence relation will usually have those same two. Now, whenever we can, we'll try and lump cases together. So we did this actually in our pseudocode, but if we had 2 or 3 different terminating cases here, we might say, well, which is the most expensive of those? Remember, we usually wear our worst case analysis hat, meaning so we want to measure the most expensive case, and we'll take that one as our stand-in. We're going to do this. We're going to split our two cases. It's going to be the terminating case and the recursive case. And we're going to, well, let's just start with the terminating case. Let's see how many operations are carried out. Now, let's go back, a few videos to when we were talking about this for iterative algorithms. We want to try and count every single operation that we can, increments, comparisons, arithmetic. In this case, to start out, we also want to count the function call. One of the reasons why counting the method call or the function call is important is now that we're into recursive analysis, we realize, hey, a lot of the operations we're carrying out are actually these method calls, these function calls. Okay, and even though I'm going to be counting them as one, if you really look under the hood, a method call or a function call will often take more than one operation, not just more than one, but a sizable constant, partly because the function call isn't just about moving into the function, it is about allocating some space for local variables. It is also about storing the local variables of the calling function so that when you are done with this function, you can get back to the state that you were in before. So there's a lot of other sort of minor operations going on when you make a function call. Now, as I mentioned before, depending on the sort of perspective we're taking in our analysis, we might start lumping a lot of these machine level operations into one operation, and that's what I'm doing here. I'm going to say one method call on the way in. Then what else again in our terminating case? If we're in the terminating case, even though we have our worst case hat on, we're assuming this is the case we're in. We're not going into the else. Yes, the else is worse, but we're assuming in the terminating case that n is less than or equal to 1. So if n is less than or equal to 1, we did one operation to get in, we did one operation on this comparison, but that comparison came up true, so we return, and that's one more operation. So I'm going to call that 3. So when n is less than or equal to 1, we do 3 operations: the method call, the comparison, and the return. Okay, good. So that leaves the recursive case. What happens in the recursive case? In the recursive case, obviously, we're not going to trigger this one, or rather, we're going to trigger this one by entering the else branch. So we'll get the one method call. We still do the comparison, one comparison, but then we enter this branch. Now, when we get in here, we realize, oh, wait, this is a recursive call here. So for me to figure out, for instance, how many operations there are on this line, I need to know how many operations are carried out by this recursive function call. And I don't know how many operations are carried out by this recursive function call because that's what I'm trying to figure out right now, is how many operations are carried out by a call to this function. But luckily, we have this mathematical formalism, T of n. So even though we don't know right now how many operations this recursive call is going to take, we have a name for that. We don't know what the number is yet, but we have a name for that number, which is T of n minus 1. And how many steps is this recursive call going to take? Again, we don't know right now at this moment, but we have a name for it, T of n minus 2. So when we put this together, when we start calculating how many operations are carried out in the recursive case, we need to split them into two kinds of operations: the recursive ones and the non-recursive ones. The recursive ones, we're going to use our special names for them, in this case Tn minus 1 and Tn minus 2. But for the non-recursive ones, we'll just count them up. So we had 1 for the method call, 1 for the comparison here. And then I'll just be a little bit careful here. We have a minus, so I'm at 3 now. We have another minus, I'm at 4 now. We got the plus, that puts me at 5. And then we were counting the return as 1 as well. That puts me at 6. So I'm going to count 6 extra operations. I call this the extra work sometimes. Okay, extra because it's the non-recursive stuff, the extra work we do other than the recursive work. And then we need to count the recursion. Well, we already mentioned this one. Because there are 2 recursive calls, we'll call them Tn minus 1 and Tn minus 2. And here, I'm just summing their costs together because we make both recursive calls. We first make the first one here, and when it's done, we make the second one here, and so we'll add them together. So what we've got here are the pieces of the puzzle, and now we just need to put them back together, which is to build our recurrence relation here, T of n. What is T of n equal to? Well, we split it up depending on what n was. If n was less than or equal to 1, we said it was 3 operations. So that's our first line here. If n is less than or equal to 1, it takes 3 operations. However, if n was greater than 1, in this case, we had our recursive calls. It took the amount of time it took to do our 2 recursive calls, Fibonacci n minus 1 and Fibonacci n minus 2, expressed here as Tn minus 1 and Tn minus 2. Plus we did 6 extra operations. We did the minuses and pluses and so on. We did 6 other things to get here. Now this function, this recurrence relation I should say, expresses the runtime of our Fibonacci sequence when called on input n, but it doesn't actually tell us in a nice convenient way, I guess is the way I'll put it. It doesn't tell us in a way that we can immediately say, oh, well, t of n is obviously big theta of n squared, which in this case it is not, just to be clear. This t of n, as I mentioned, the runtime of this Fibonacci should be bad. I said this is a bad way to calculate the Fibonacci sequence. You should use a loop or something. That's a better way. Recursively doing it this way, we end up duplicating a lot of work. Again, if you want to, write the code and go check it out for yourself. You'll see the work is getting duplicated a lot. But in particular, it ends up taking an exponential amount of work. So the theta bound here is more like 2 to the n. It's not quite 2 to the n, but it's in that range. Okay, it's between square root of 2 to the n and 2 to the n. Okay, and there's a lot of cool, interesting things about what the actual bound is, because the Fibonacci sequence is a really cool sequence. But I think I've said enough in this video, so if you're interested in learning more about the Fibonacci sequence, I think I've got another video out there that does go into more details about that, so go stay tuned and find that. I believe it's in the Design and Analysis playlist. But otherwise, in this playlist, and the next thing I'm going to do is I'm going to do the same type of analysis we've just done here for a different recursive function, and then we're going to see how we can take this t of n further. Now, we're not going to do it with this one, partly because this one is a little bit more tricky and a little bit more painful to get it where we're going. Okay, so stay tuned in that next video where we take a look at that. So thanks a lot for watching, and we'll see you in that next video.